Okay. Okay. So this semi-classical theory is related to Drude theory, right? Because Drude theory allow us to somehow come out with the electrical conductivity. We can measure the sigma in the end. All right. So it related to the how electron motion in our solid. And we, of course, we know we have discussed about Drude theory. It is a classical approach, and it assumes that electron collide with the ions. All right. So the scatterers, the main scatterers is ion. This is what Drude theory is about, and it can explain the Ohm's law. Um, we can calculate the sigma, right? The electrical conductivity, and also we can also, in the end, we also discussed about Hall effect based on the Drude theory, and also how in the end we come out with the Widman-Franz law, right? Widman-Franz law, which is the relation between the sigma, which is the electrical conductivity, over the thermal conductivity, and we know it is a constant. All right, and it we know that Drude theory unable to give us the electronic heat capacity, right? And we don't have that dependency on the electron or the electronic contribution to the heat capacity, the CV. We also have seen this. And later on, Sommerfeld, he actually applied the same approach based on the Drude theory, but he just make the electrons basically obey the Fermi-Dirac statistic. All right, and by doing so, we have seen that Sommerfeld theory able to explain large mean-free path, and we can come out with the electronic heat capacity, but of course with the exception of a few metals. Not all can be covered by Sommerfeld theory. So in this theory, it's a semi-classical theory of electron motion, and it's actually a generalization of Sommerfeld theory on periodic potential. All right, we still going to study about the electron motion. Right, we are interested in how electron moves inside our solid, inside our crystal. So inside the crystal, we have this periodic potential, right, given by the ions, and the periodic potential is follows the periodicity of the lattice that we have, and this theory will provide us anomalous behavior of the electron dynamics, like I mentioned before. All right, it is possible to develop a fully quantum mechanical theory approach of electron transport in solid, but we will not look at it in this course. Of course, when we apply fully quantum mechanical approach, it's going to be more closer to the real experimental result, right? So why semi-classical? Because the first is because it is very useful. It leads to important insight into the transport problem, especially in metal. We're going to see after this what we can do with this theory. And secondly, it is based on WKBJ approximation in quantum mechanics, right? So we're going to look first, we do some revision on what is the approximation or WKBJ approximation in quantum mechanics. Wait a second, it didn't move. Okay, now it moves. Okay. All right. Right. So WKBJ approximation in the quantum mechanics or in mathematical physics says whenever we have a wave packet with a smooth envelope, where we can calculate its position and momentum as long it is within the limit of Heisenberg uncertainty principle. Therefore, our particle behave according to the classical equation of motion. So this is the origin of the semi-classical, right? We apply the quantum mechanical approach by using by employing the matter wave concept, and if the solution of our wave function is it takes in the form of wave packet with a smooth envelope, right? So therefore we can imagine this one wave packet can be represented by the particles. In this case is electron. So we can calculate its position and momentum, but of course we need to consider the Heisenberg uncertainty principle. And so therefore we can apply the classical law of mechanics to our particles. So basically all the Newtonian mechanics can have the second equation of motion, Newtonian mechanics, and so on. All right, so it's given by this equation, second equation of motion. So if you look at the psi, the wave function for this wave packet, it will give us in this term, so gk eik dot r minus h bar k squared over 2m and t. So this is general wave packet. This we haven't applied this for the case of electron inside the periodic potential. So this is in general case of WKBJ approximation. So since we have assumed, let me change my color. So because of the semi-classical approximation, so therefore we can write this momentum h bar k is equal to the mv, the momentum given by the classical mechanics or physics. And by doing so, we can write the expression of velocity. All right, the velocity is equal to the time derivation of r. R is the position or the coordinate vector. All right, with time, and it's equal to h bar k. K should be a vector also, divided by m. All right, and second equation of motion, so we can write it as this equation: h bar k is time derivative of the k momentum or the wave vector equal to negative e charge of electron. E is the electric field, 1 over c speed of light, v is the velocity, and h is the magnetic field. All right, so we can apply the second equation of motion to make our or as we go along with this theory. So now we apply the WKBJ approximation for electron moving inside the periodic potential in the, like the one that we have in our lattice, right? In the crystal, we can construct a wave packet that looks like this. Is almost similar to that equation before, the general one, but okay, the first term is the envelope, represent the envelope of the wave function that depend on k. All right, and that is, it carries the information about the periodicity of the envelope, the high the low frequency one. All right, and inside the wave packet we have higher frequency, right? And this is what given by the block eigenstate for the electron in solid, given by the second term that we have here. All right, this is the energy of the band and referring to the what band of that we want to study. And so our second equation motion now can be written as this, and the velocity term, and which is with respect to the k, is equal to the time derivative of r, and is equal to 1 over h bar, the d energy, all right, divided by dk. It's no longer constant u like we have in the general case before. V, sorry, no longer constant v like we have in the general case before. All right, so the velocity changes with respect to the change in the energy. All right, it depends on the energy, and energy depends on the k value. And the second equation of motion can be written like this: h, this is time derivative of k, negative e. So this is basically the Lorentz force that the electron feel. And now we are actually referring to the electron motion in the same band, right? And if it is if it involve the transition from one band to a higher band, or between two bands, so that's going to be another story. So now what we our theory will only cover electron motion in the same band, right? So basically the same band that within our first Brillouin zone, we can see that it looks like this. Right, this is the energy dispersion relation. This is pi over 2. This one we know is a negative pi over 2, right? So we only assume electron motion inside the same band. So what is the limit of the validity of this theory, this semi-classical theory of electron dynamics? So there are 3 limits. Actually, there are 2 limits. Two limits. The first is the applied field. The applied field on our electron must be weak enough, right? It can be in terms of the electric field, also magnetic field. It must be weak enough. And how weak is it can be related to this relation. So E, the electric field multiplied with A is much less than the change in K, which is referring to the band gap, divided by EF. This change in the K squared divided by EF. So that is the limit for the electric field. For magnetic field, we can write the limit as given as this: h bar omega c. Omega c is the classical cyclotron frequency, and inside this term, this coefficient, we have this h, which is the magnetic field, right? E h magnetic field divided by m. M star is the effective mass. So the similar concept that we have discussed during our tight binding calculation, the effective mass, right? Divided by c. And this is called classical cyclotron frequency, and it should be much less compared to the same term that we have on the right hand side as the electric field limit. So the band gap squared divided by the Fermi energy. All right, this is the limit. We're going to see how this is related later on. Okay, so the second limit is for alternating current field. That means our applied field is no longer constant over time, so it's alternating. So at certain omega frequency, so h bar omega need to be less compared to the band gap. So the condition of 1A, which is this one, and these two are well within the normal experimental condition. That means we don't need to worry about this if you want to apply this theory in our experiment. But this condition is easily violated, which the term is called magnetic breakdown. All right, so the magnetic field, the applied magnetic field is higher compared to the right hand term that we have here. So in that case, this theory is no longer good for our experimental or that particular experiment that we are doing. So based on these two limits, or the limits of validity, all right, based on the semi-classical theory of electron motion, in order for this theory to be valid, the electron must stay in a given band, which is whenever the electric field is too high or the electric field very rapidly, it can give the electron enough energy to make transition between the band, which is not what we cover in this theory. So again, we only consider the electron motion along the same band, right? So whenever we have transition between the band, like in the case of the semiconductor and so on, like we discussed during our Fermi golden rule, right, in the I think last week lecture. So that involved the transition. So that is not what we are doing in this theory. So these two limit actually is so this is the implication of the limits. So we don't want the field to be too high or the frequency of the E to change or to vary rapidly, so that the electron will still be in the same band. All right. So in an ideal solid, with no imperfection, electrons simply follow the semi-classical theory. This is the second equation of motion. the Newtonian one that we have applied for electron, for the case of electron in periodic potential. And in this case, the energy and momentum is conserved, all right, throughout the electron motion. But due to the presence of an imperfection in real solid, we need to consider the relaxation. All right, so this is, we can say, if our real solid will not be a perfect or ideal crystal. All right, we're going to have imperfection and so on, and this will contribute, or this will affect this electron motion in our solid. And that's why in the real solid we need to consider this term relaxation, right? And what the process that happens is actually the scattering. So the electron are not as free as we thought it be. It will have some scattering or collision with other particles, and so therefore we need to consider this in our theory. So based on this semiclassical theory, there are two questions that need to be solved or to be answered. All right, the first is how electron behave between scattering. So we know in a real crystal we're going to have a scattering. All right, we're going to have a scattering, and by using this theory, how can we quantitatively analyze the electron motion in between the scattering? And the second question that we want to answer, we want to discuss in this theory is what is the nature of the relaxation in solid. So what types of collision that the electron basically undergo, all right, in a real solid. So we can have a lot of possible scatterers that we can have in a solid. All right, to answer the question number one, we need to look at the consequences of the semi-classical equation of motion. Right? And the first statement that we can make is field band is inert. So whenever we have a field band, the case of a tight binding method is going to be look like this, and same goes with the when we saw about the nearly free electron. Right? This is the energy, the band structure that we will have. So if the whole band is occupied or filled, let me do like this. So this whole band is occupied, it's filled. So there will be no current. So electron, we can say it doesn't contribute to the transport phenomena, referring to the electron transport. Right. So whenever we have this band which is fully occupied, it will not contribute to the transport phenomena. So to prove this, we need to come out with the current, right, J, and is equal to negative E. We need to apply this integral over the Brillouin zone, because this is where the states is being occupied. D cube K divided by 4 pi cube Vg is the group velocity of the electron. All right, we need to do this integral, and this group velocity of the electron inside a solid, if you look back up here, we have this term, right? So it's no longer constant velocity, but rather the velocity change according to this term, the En divided by dk. So what we do is we just insert that in, where are we just now? Okay, here. Right? So we still have this integral over the Brillouin zone. And let's apply for the case of 1D, right? For the case of 1D, since the energy is a function that is periodic on the Brillouin zone, so therefore this integral over the Brillouin zone vanishes, which means the J will be 0. Right? So because of this energy is a function that is periodic on the Brillouin zone. Remember, before we can also write in the Brillouin zone, or illustrate the Brillouin zone in the repeated zone scheme. Right? So we have this first Brillouin zone, and so on. So we have this okay, so we're going to have the same. If you have higher, going to be like this, and so on. So it's a periodic function on the over the Brillouin zone. So therefore, this integral vanishes. So let's look at the 1D, how this can vanish. So for 1D, this the J, the current, we are from here, this is actually referring to 3D. This is 3D. So we want to prove just by using 1D because it's much simpler. So our equation for 1D is to become negative E pi. We do the integral from negative pi over 2 until pi over 2. This is within the boundary of the Brillouin zone. All right. And here to become dk over pi only instead of cube just now. 1 over h bar dek over dk. And we can take out the, I think we should have pi here. So I'm missing pi. All right. We can take out pi and also h bar. And we end with the E energy term. We can insert the value of K from pi divided by 2 or negative pi over 2 until pi over 2. And since the energy looks like a cosine function, and indeed it's a cosine function near K is 0, right? It looks like a cosine. So therefore this term will be 0, right? Pi over 2 is 90 degree, cosine 90 degree is 0. So therefore, field bands are inert and can also be understood as same number of electrons moving from left to right and right to the left. So this is where the electron already occupied all these K states, right? And the number of electrons moving from left to right is equal to number of electrons moving from right to left. So there's no net current or electrical charge flowing there. So there's no current whenever we have a field band. So this is actually from K. K is the wave vector of the wave. And since K can be negative and positive, like we have here, positive and negative. So if K is negative, it means that the wave moving to one direction. If it's a positive, that means it moves in the opposite direction, right? So here we have same number of electrons moving from left to the right and right to the left for the case of field band. All right. So let's discuss about this motion in applied DC current. I mean the no current, sorry, DC field, electric field. And whenever the H, whenever the magnetic field is 0, and since it is a direct, and this is DC, so our electric field is a constant, right? And the momentum of the electron can be written in this equation. And now it depends on time because we need to have a dependency on time for this K now. So K that depends on time is equal to the K at T is equal to 0. And we have the additional term here that depends on T, right? So this K will depend on T, and it is linearly evolved in time with this to become the coefficient that describe the linear change in the K with respect to time, right? So if you can look at this illustration here, at T is 0, so the E is the electric field, the applied electric field is 0. We haven't turned on our electric field. And this is, of course, we want to deal with the case of partially filled band. So this is related to metal, right? So whenever we have this partially filled or half filled band, we know it is a metal. It must be a metal and should be a conductor. All right, and we want to know when we introduce our electric field, when we apply our electric field, external electric field, so what's going to happen to the electron transport in our crystal? All right, so at t equal to 0, no electric field applied, so we know it is equilibrium. So basically, same like before, the number of electrons moving from right to the left and left to the right is the same. No electric field applied. So you can imagine this as a metal, just any metal which is not applied electric field. All right, it's not part of the circuit, for example. All right, so this is what happened. There's no the net flow of electron is 0. So whenever we have introduced the electric field in that direction, okay, after some t, we know the k will be changed now because of this equation. All right. So what happened is the electron will start to march at the opposite direction as the electric field. So before it is equilibrium, now this electron move to the opposite direction compared to the electric field. All right, that's what we notice first. The first consequence. The second is the electric field cause non-equilibrium of the electron distribution compared to what we have before. It is equilibrium, you can see clearly, but now it's it's not no longer equilibrium. We can see some of the electron, right, due to the applied electric field, it moved towards the opposite direction. So now we can say we have created current, right, because number of electron moving to one direction is more compared to the opposite one. So current is generated, which is more electron move in one direction compared to the opposite direction. So we have somehow explained how the electron can the transport phenomena of the electron in our solid. But we also should expect that as more electron occupies the k states in one direction, the electron will go all the way around and come back to the original ground state. At some time, there will be no current. You can imagine if this is, for example, the electric field that we apply is strong enough, and after some time, there will be more electron to that will occupy the higher k states in one direction, and up till one point, it will start to be in this direction again. All right, because this function is periodic, so it start to occupy this back again until we can say it the current will be a periodic function, right? At some point, the current will be 0 again whenever we have this condition again, which is the number of electron moving from the or which is we have the equilibrium distribution of the electron. All right, so we expect based on this explanation of the electron transport that the current will be a function or will be predict over time with respect to time. But this is not what we observe in the experiment under the normal condition. All right, we didn't notice this in normal condition or in basically in any type of measurement, except for few cases that I will talk later. All right, so we don't see this current, the effect of current that is predict in time, and so therefore this is counterintuitive. This is not observed in the experiment at least. So we need to look back at our theory. So what went wrong? The answer is we did not take into consideration the effect of collision in real metal. So what we have in our explanation before here, we didn't introduce the scattering, right? The relaxation approximation. So therefore, we need to apply the relaxation approximation to this explanation. Okay, so which is the same time the electron moves in one direction, there will be process where electron from higher energy states are brought back to their original states. So let me draw again. Maybe I need to change the color. All right. So whenever we have this is occupied up till here, at the same time the electron occupies the state in the opposite direction, it will also experience a process where it is brought back to its original uh, states, right? So it is actually like a restoring force for the electron. Whenever you want to go to one direction, we're going to have that the effect of the collision basically, which causes the electron to be brought back into the original states. So because of this collision, that is why we don't experience this periodicity of the current in time, right? Because of this, in real metal, we will never get a perfect crystal, right? Or ideal crystal. So never. So we always have this. Collision in whenever we talk about the transport of electron in the solid. So these act by balancing the effect of the applied electric field with the collision and scattering. Right. So what the statement that we can make here is collision restore the equilibrium or the steady states. So whenever we have applied the electric field and we have the same explanation that we had before, the electron start to occupy the opposite direction compared to the applied electric field. And because of this, it creates non-equilibrium, right? And it is actually not a single process. We also have simultaneous process, which is the electron is actually brought back to their original states via the collision or causes by the collision that the electron experience. Right. At this point, we didn't talk about what types of collision that the electron underwent or undergo, right? And that is, remember before, we have two questions that we want to answer, that we need to answer or we need to solve by using this semi-classical theory. So, however, the phenomena of periodic current with time was observed for a sample which are close to ideal and pure crystal structure in metallic sample at low temperature to avoid phonon collision. So this actually, like I mentioned just now, in the normal condition of the experiment, we didn't see this periodic current phenomena. But whenever we try to reduce the crystal defect or we reduce the imperfection that we can have in the crystal as much as we can in a metallic sample, and we need to apply the low temperature, we need to basically do the experiment in a low temperature to avoid the phonon collision. We're going to see this periodic current with time, and this is in fact not observed until not very recent. I think it's 1990s something, right? So this effect of periodic current with time, which confirm that the relaxation theory that we relaxation approximation that we have discussed before. All right. So whenever we don't have this collision or the collision is minimal, we will observe the current will be periodic over time, and this phenomena is called block oscillation. All right. So at this point, it is convenient to introduce the concept of holes when the band is nearly filled. All right. So we're going to see how the concept of hole can emerge in our semi-classical theory of electron motion, because we know the contributor for the current is the electron. So that is what we have applied so far, right? So in our equation of the current, we have this negative E, which is referring to the electron. All right, the electron contribution towards the current. And when we apply for the case of a band which is nearly filled, so this is empty, so the band is nearly filled, we can do the integration that we did just now. We want to find the current caused by the field electron. right? And we can also write this as the integral over all states, all over the brilliant zone, minus the empty states. So we're going to end up with this field states, right? The integral that we did before, right? So whenever we have done that, we have a negative sign here, negative sign here, it become positive. And we do the integral over the empty k, empty states. This is the same equation like before, the current d cube k. This is of course for 3D, for pi cube 1 over h bar dek over dk. So this equation is real mathematically. So what does this mean? This means that we can view or we can expect at least the current is also contributed by a positive charge, just like we think how electron contribute to the current, right? So this equation is a real equation, so therefore here we no longer have a positive sign for the charge, we have a negative sign, we have a positive sign for the charge, and it has the same charge as the electron, but it's just the opposite charge. And so we can say that the current can be carried by electron and also holes. So in practice, if band is half filled, we use electron, right? Because electron is the major carrier. If band is nearly filled, we use hole. So this also you can relate this with a P and N type semiconductor. So in P, we have hole as the dominant charge carrier, and in N type of semiconductor is electron, which is the dominant charge carrier. All right, can we take a 10 minutes break maybe? Can, right? So tomorrow, Faisal, you want to join us? Abdurrahman? Abdurrahman said you want to join, right? How about Faisal? All right, 11. Omar, I will ask him directly later on. Okay. So regarding the, all right. Omar is sick. So maybe only two of you can attend tomorrow. For the visit. Right, 10 minutes break. We will continue to 56. Okay, let's continue with our semi-classical theory of electron motion. And if we look back, we actually try to solve the first question here, which is how electron behave between the scattering. All right, so this is what we have done before. The first statement that we have introduced is about field band is inert, and we also have proven that for the case of 1D. And next we applied the constant electric field. Wait a second. Right, we have applied for the case of electric field is constant and the magnetic field is zero. We have seen current is generated. Okay. And now we're going to see about the case of H, which is the magnetic field is a constant. It's a constant field. And the statement that we can make here, same like before, is the component of the momentum, the wave vector k, which is parallel to the applied magnetic field, and Ek, the energy, are constant of motion. So it's constant. It will be a constant parameter throughout the motion of the electron. So this statement is in agreement with the classical physics. When a charged particle moves in a magnetic field, it experiences Lorentz force that is always perpendicular. Therefore, the component of K along the H along the magnetic field always conserve or doesn't change, right? And given by the Lorentz force, given by the left hand Fleming or the right hand rule, right? We can see that the force is always perpendicular to the applied field. So therefore, the component of the K, which is along the magnetic field direction, is always conserved and doesn't change. So therefore, we can write this as in this form, right? K, which is component of K, which is parallel to H magnetic field, is equal to the unit cell of the magnetic field multiplied with the dot product between the K and also the unit cell, unit vector for the magnetic field, right? Given by the H hat. So H hat is equal to the vector of magnetic field divided by the magnitude of the vector. So therefore, our new equation of motion can be written in this form. This is of course for the case of a constant magnetic field, right? And we want to prove the statement that we have here before in the box. Okay. So since the dot product we have here will be always 90 degree, right? Yeah. So dot product has cosine, so cosine 90 degree should be 0. So whenever, so therefore we can write this, the time derivative of k, which is parallel to the h, will always be 0. That means it is constant over time, constant of motion, we can say. And similarly, we can also see or show that the dEk, the energy over dt, is also 0. So both of this term is always conserved. Right? This is not we're not going to discuss this in greater detail, but just to introduce you to the case of the magnetic field, constant magnetic field. Right? So these two constant, these two parameters will be a constant of motion. As a result, electron in magnetic field move along curve given by intersection of surfaces of constant energy with planes perpendicular to magnetic field. So whenever this is like we have before in Fermi energy, if you have a sphere Fermi energy, spherical Fermi surface, so it's a sphere, and whenever we apply the magnetic field in this direction, the electron will move along the curve given by the intersection of surface of constant energy. All right, this is the Fermi energy referring to the surface of constant energy. All right, so it will move along this curve with planes perpendicular to the magnetic field. So this leads to, or this concept leads to a very powerful probe of the energy spectrum of solid, which goes under the name of magnetic oscillation. Right? By using this magnetic oscillation, we basically can recreate the surface of constant energy. For example, for Fermi surface, right? For spherical Fermi surface at T is equal to 0 Kelvin, for example. So we can recreate the Fermi surface by using this phenomena, magnetic oscillation. All right. So now we have covered about the question number 1. So now let's go to the question number 2. Right? And the question that we want to solve, or the problem we want to solve, is what is the nature of relaxation in solid? So remember, before we have seen that the relaxation plays important role in the transport phenomena of electron, wherever that creates or that acts as a restoring process for the electron. That the collision or the relaxation is the process or the phenomena that will bring the electron back to its original states. But we don't know what kind of relaxation, what kind of collision that we have for the electron in periodic potential or in the solid. So there are several things that we can relate. The first is this electron can collide with the lattice ions given by the Drude theory. So this is what Drude theory is about, or Drude theory is about. So it assumes that the electrons collide with the ions, all right? And in fact, this collision, this electron and ion collision, is the dominant scatter in metal. But this is wrong. Rather, based on the quantum mechanical approach, because Drude theory is a fully classical, it treats electron as a classical particle, as similar to what the gas molecule, all right? And based on quantum mechanics, we can find the eigenstates of electron in this periodic potential. And the group velocity of the electron in ion periodic potential is non-vanishing. For the case of a nearly free electron and so on, we can still solve for the eigenstate when we introduce the periodic potential, right? And we can also get the group velocity. The group velocity is not 0, therefore it's non-vanishing. So this is not correct. This statement is not correct. That means the ion is not the dominant scatterer in a metal, but rather we can still have that, especially according to the Bloch theorem, the electron, the wave, right? The wave will have the term which has the same periodicity with the potential, with the periodic potential. This is wrong, right? This is what based on the Drude theory. So we can also relate this relaxation with the electron-electron scattering. That means the electron collide among themselves, the electron-electron scattering. This is weak, all right? This is weak. And also we can have a magnon. This is another quantum particle. We can this scattering can also happen, but this is also weak. So these two can be neglected, right? The contribution of these two types of scattering, or two types of scatterer, which is the electron and magnons, can be, it's not the dominant scatterer in a metal, which acts as a restoring process that we have discussed earlier. And we can also have another two, which is the first is disorder that we have in the crystal, such as a crystal defect, impurities, imperfection, and so on. Right? Impurities can go by the substitutional impurities, and also another one is, what's another one? I forgot. When you replace, right? And also we can have other types of defect or imperfection that we have in the crystal. So this can be a dominant scatterer for the electron. And secondly, the second dominant contribution is from phonon or lattice vibration. So this is what give out the heat, basically how heat conduct the heat transport in our crystal. So the lattice vibration, right? When we use our quantum mechanics, so we can treat this vibration with in the quantum mechanics, and this we come out with this phonon, right, which is the quantization of the vibrational energy of the lattice, right? And this can be another dominant scatterer for the electron in our solid. So this effect, this dominancy of these two effects can be studied by varying the temperature, right? So basically we can say that these two effects balance off over the temperature variation. So for the phonon case, whenever we have high temperature, whenever our solid is high, is hot, that means high temperature, this scatterer, this phonon scatterer will become a dominant. So whenever the temperature is very low, so this disorder that we have in the crystal will play more dominant role towards the relaxation. All right. So we're going to include collision through the relaxation time approximation. So based on the relaxation time approximation, it says that electron in the solid experience a collision in time interval dt with its probability dt over tau, and tau is a relaxation time. Right? So this is basically we need to apply this relaxation time approximation in our semi-classical theory of electron, so that in order for it to be complete. So this is more now we're going to discuss about how we can relate the macroscopic phenomena, macroscopic parameters. For example, this sigma and also kappa. Sigma is the thermal conductivity, and also kappa, same like we have done during our analysis on the Drude theory and Sommerfeld theory. All right. In the end, we go to the Widman-Franz when we talk about the ratio between the psi and also kappa. All right. So this theory relies on the concept of non-equilibrium distribution function, the one that we have seen before. So whenever the distribution of the electron is non-equilibrium, so we have a current. All right, we have a current. It can contribute to the electrical current, and also it can be contribute to the thermal current. All right, since we know the thermal conductivity can also depends on the electron. All right. All right. So this is the non-equilibrium distribution function given by this, and it's equal to the number of electron in the nth band at the time t in the phase space volume around the point Rk. All right. So basically, we want to solve this term, this non-equilibrium distribution function, and in the end, we want to find what is this sigma and kappa. All right. So the result for Gn, if we work this, this actually I tried to find in the Kittel book, but I couldn't find this topic. but this is in Ashcroft book, right? This is another solid state theory book. You can also find the PDF of the book online. It's very easy, same like the Kittel one, right? The in Ashcroft book, it is in chapter 13, chapter 12 or 13, 13 maybe, right? So we're not going to do the derivation. So when we want to solve for the Gn, the non-equilibrium distribution function, we assume the following: we assume the uniform system and weak, slowly varying applied field. This is goes back to the original limit for the semi-classical theory that we have discussed earlier. Secondly, is the scattering is independent of R, so the tau, right, the relaxation time only depends on the energy, right? No longer depends on R. We can say that we can translate this into having a homogeneous sample, right? So homogeneous sample, it is not dependent. The scattering is not dependent on R, on the distance. So rather the scattering is we can say is homogeneous, right? And the third is the temperature variation is small. So this is what we assume when we want to solve for the Gn, the distribution function just now. So finally, we got this term. It's very long term, right? G and K. This is Fermi-Dirac distribution function. This is the tau that we have just now. This is Fermi-Dirac distribution function over dE. This is the velocity of our wave packet. All right. So this is the electric field that or the applied field in form of electric field. And this we have the electrical potential, right, that we have introduced in the Fermi-Dirac statistic, mu. And T is the temperature, and this is the temperature gradient, right? Temperature gradient. And the H, which is the magnetic field, is actually translated into the velocity. Whenever the magnetic field change, this velocity will change. So we're going to have a different distribution. So this equation is also known as a linear response theory, and it is surprisingly good agreement with experimental results. But we can say it's for metal, right? Because this is transport for we are considering transport of electron in the same band. So therefore, this is we can see why this is a good agreement with a metal, or can be used to for the case of metal. All right. So thermal and electrical current, right? So this equation we have seen before for thermal, for the electrical current J. For the thermal current, we write it as JQ, right? So the electrical current is given by negative E, the same equation that we have before. In 3D, we have D cube K over 4 pi cube. So now we have this Tn, relaxation time, okay? It depends on E energy and K. And Gn is what we have here, right? The distribution function that we have here. This is what gives us info on the which states is occupied, right? So if we want to solve for the J, we need to basically follow this derivation here. And if you want to solve for the thermal current, this is the equation that we need to use. So for a metal at low temperature, all right, at low temperature, and the temperature is constant, it doesn't change. The change in temperature is 0. We know we can write this the relation between J and the electric field is a linear, right? And the coefficient here is given is the electrical conductivity is a sigma. Sigma is electrical conductivity. And when we apply this equation that we have before, Gn, to find the sigma, based on all the approximation that we can do, we can write this as E squared tau. We need to do this integral and so on. And in the end, we can recreate the equation of the electrical conductivity when we discuss about Drude theory. So this is a Drude formula for the electrical conductivity. So in the end, we end with the same equation for the electrical conductivity. Ne squared tau divided by m star, which is the effective mass of the electron. Okay, so as for thermal conductivity, this is kappa. All right, we know the relation between this one is linear, the thermal current, and also this gradient, temperature gradient, negative of temperature gradient is linear, and the coefficient that we have here is kappa, and kappa is given by this equation, pi squared divided by 3, kb is the Boltzmann constant, divided by E squared T, the temperature, and we have this this electrical conductivity. So when we move these two on the right hand side, we can write this as kappa divided by sigma, is T, right, equal to the right hand side, we have all constant. So this is consistent, consistently can be produced in experiment, that this the ratio between the kappa and also the sigma is constant. So in general, this theory works for all metal but violates semiconductor and insulator. So if we want to study about the transport and semiconductor insulator, we need to apply more advanced theory, right? But this theory is very useful for metal, all right? It's good enough when we want to study about the about metal, and as what we have seen before, we can use, if we change the magnetic field, for example, we can study the Fermi surface or the surface of surface of constant energy. Yeah, this one. All right, and it turns out that this theory works well in this experiment or in this technique, and we can also explain the how electron move, all right, or the transport phenomena of electron whenever we have applied the electric field, and based on the non-equilibrium distribution of electron in our within the Brillouin zone, we can see how the current can be generated. All right, and I think that's all what we have today to discuss.